Okay, students, now we'll study common emitter configuration, which is also known by the term CE mode. So in this common emitter configuration, we consider a PNP transistor again, right? In this PNP transistor, the emitter section is basically grounded, and the base section is the input of this transistor, and the collector section is the output of this particular mode, right? So in this mode, obviously in the base emitter mode, we are going to put a forward biased, right? So this is P, this is N, this is P, right? So if this is a PNP transistor, then in this PNP transistor, these N should be connected to the negative terminal of the battery, and the P should be connected to the positive terminal of the battery in order to make the emitter base junction forward biased, and the collector base junction should be reverse biased. So the P side of this particular P side of the transistor is connected to the negative side of the battery, and the P side of this is connected to the positive side of the batteries to make it a reverse bias. So now we'll understand what is the operation, how is the operation going on, and what are the input and the output characteristics of this mode, right? So over here, if I see, then IB, IE and IC are the current flowing direction that is happening in this transistor circuit, which is already discussed in the previous video lectures. You can go through them. And the VEB and the VCB over here again have an impact on the early effect, right? When VCB is increased, the early effect, due to the early effect, the collector current will also be increased rapidly. The early effect is also described in my video lectures. Please go through that video lecture once if you have not seen that video lecture. Then this entire circuit will lead you a gain, right? Since due to the early effect, there is a kind of gain of current that is happening in the transistor circuit, and this gain is given by the term beta. Beta is the current gain in the common emitter mode, and this is the ratio between the output circuit to the input circuit of this transistor diagram. So in the output circuit, the current is IC, and the input circuit, the current is IB, right? So it's a ratio between IC and IB, right? So in other words, we can say that IC is equal to beta times of IB. That means the IC, what is the collector current? The collector current is basically IB, but it is not only IB, it is beta times IB, where beta is the current gain, or you can say this is the DC current gain in the common emitter mode, or it's a forward current transfer ratio, right? So whatever is being said, in the common base mode also, there was a current gain which was given by alpha. This alpha is equal to IC by IE, because in the common base mode, if you remember, the base was the one which was common between the input and the output circuit, but in the common emitter one, the emitter junction or the emitter one or the emitter side is common between the input and the output circuit. So in the common base region, in the common base mode, the base was common between input and output circuit. So the output was again IC and the input was IE. So obviously then IC was equal to alpha times of IE. So IC is basically alpha times that of IE. So the amount of current gain that is happening in a common base mode is basically given by this particular expression for collector current. And alpha is again the DC current gain in CB mode, right, in common base mode, and beta is the DC current gain in a common emitter mode. So from this, it is clear that the circuit is basically producing a gain, right, a gain of current that is being produced. Now we'll quickly go to the input and the output characteristics of this particular transistor. Now we move on to the input characteristics. The input characteristics is a plot between the input current and the input voltage. The input current is IB, this is the base current, and it is measured in milliampere. And the output voltage is base emitter voltage, which is VB, which is measured in volt. since IB and IC in a PNP transistor are negative, so obviously IC is negative means VC is negative, and since IB is negative, so obviously VBE will be negative. If you cannot understand the convention or sign convention that I am using over here, then please refer to the sign convention video that I have already given of a particular transistor, right? So if I look into this graph, then it's very clear that VC is the output voltage, or is acting like a parameter in this particular graph. So as we increase VCE for a fixed VBE, the IB currents move up, right? So the IB current moves up. Why does it show characteristics similar to this particular graph? Because due to the effect which is known by the term early effect, which I've again already discussed. If you don't know early effect, please go through the early effect video lecture, then you'll understand what is early effect. So if I now jump to this point, then due to the early effect, the effective base width decreases, and due to this, the recombination at the base side also decreases a lot. So the holes now jump from the base section to the collector section. A number of holes jump from the base section to the collector junction, and due to this, the whole current increases a lot, right? So obviously the current in the base, or the base current, will increase sharply. What happens is that a large number of holes now moves to the collector junction. Why is it so? Because the effective base width of the base section reduces, thus reducing the majority carrier, which are electrons in this case, right? So the recombination which was happening before between the holes and the electrons in the base junction also reduces very sharply, and due to this, a large number of holes which should be minority carriers in the base section, because base section is an N type, so majority carriers are electrons and minority carriers are holes. But now, due to the reduce of the effective base width and due to the reduce in the recombination process in the base section, a large number of holes are basically residing in the base section, and due to the vibration that is happening between them, they get even more excited, and a large number of holes now jump from the jump the depletion region across the base and the collector junction and moves to the collector section, and due to this, there is a sharp increase in the base current, and that is what is shown over here. There is a sharp increase in the base current as we keep the base emitter voltage constant and increase VCE. Now we move on to the output characteristics. The output characteristics is a plot of the output current versus the output voltage. The output current over here is IC, which is measured in milliamperes, and the output voltage is VC, which is measured in volt. Right, so since IC and IB both are negative in case of a PNP transistor, so obviously the VC is negative, the IC is negative, and obviously the IB is also negative in PNP transistor. So IB is a parameter, that means for a fixed value of IB, we will basically note the change in IC, which is the output current. In the input characteristics, we were interested in taking the current value of IB, because IB was the input side of the transistor in a common emitter mode. And now when we are dealing with output characteristics, we will be interested in taking the value of IC. So if you observe this particular graph more closely, then these lines are not completely horizontal lines, because since the effective base width reduces a lot, so the number of recombination or the rate of recombination also decreases a lot. So a large amount of holes are now crossing the are now crossing the depletion region between the base and the collector junction, right? The number of holes that were coming from the emitter junction previously, when the VC was not increased and the effective base width was not reduced, then a number of holes which were coming from the emitter side were recombining with the electrons in the base section. Now with the decrease in the effective base width, a large number of holes are coming from the emitter side and are quickly recombining with the small number of electrons that are present in the N side, and the number and the concentration gradient of holes which are minority carriers in the base section increases a lot, and due to this a large number of holes now crosses the depletion region across the base and the collector junction, flowing a large amount of collector current coming from the emitter side as well as the reverse saturation current that is happening in the collector base junction, right? So due to this, the collector current increases very rapidly. So for a fixed IB, we can easily note that the collector current is increasing very rapidly. Then we will basically go into the section of active region. In this graph, what section of the graph is the active region? The active region is just above the zero, above the 0 point or above the zero value over here, from this section till this section is the active region, right? This section to this section is the active region, but the transistor is working like a normal operation, right? What is the saturation region? It is the point before the cut-in voltage, right? This section, if I closely observe this section, the portion that I am marking out is the section that is the saturation region, where both the emitter base junction and the collector base junction are forward biased. Here the collector base junction value is almost close to zero, so it's not negative, right? So if it is not negative, obviously then both the emitter base junction and the collector base junction are forward biased, and if they are so, then this region, which is just before the cut-in voltage, where the IC current increases very rapidly, this section now becomes the saturation region, right? Now comes the cutoff region. The cutoff region is where the transistor is not working. Transistor is not working means we have to keep IB equal to 0. But in case of a common emitter mode, keeping IB equal to 0 will not do. What we have to do is that we have to slightly reverse bias the emitter junction. Because the emitter junction is forward biased, right? And so a number of excited holes will try to cross the emitter and the base depletion region and will reach, and some of the holes will reach the base section. And from the base section, since with increasing VC, the base section will get reduced, the effective base fit will reduce, and due to this, a small number of holes will try to reach the collector junction, and due to this, the entire process will not be completely cut off. So in order to make the entire transistor, or in order to understand the cutoff region in case of a common emitter mode, you have to slightly reverse bias. The emitter junction, so that the cutoff region is properly seen, right? This is the cutoff region where the transistor is not operating anywhere. So this is where the cutoff, this is the saturation, and this region is the active region. So this is what the output characteristics of a PNP transistor in case of a common emitter mode. Thank you.